Okay, let's get started. Today we're going to continue our canonical correlation, and I don't think we have time to do canonical correspondence, but first thing first, okay? Unless you guys are really interested, I may not give you a homework of this, but I'll give you all the code and stuff to play with, okay? And this is why this is important, okay? So right now, I can have x1, x2, x3, a bunch of x, okay? And this is, we can consider as a system input. And the system inputs are a bunch of people, unit, guides, factory, a lot of stuff. And as long as x1, x2, x3 are a bunch of real number, and write them in column, can you do signal detection theory? Can you do information theory? Can you build structure equation model? Can you build, basically I can do this for signal detection. I can do entropy or KO divergence, and I can do SEM, structure equation model, and I can do, and of course is the Bayesian net, okay? And you can of course always say that, some sort of ROC, and said my a priori assumption and do yada yada and get it done. And this is a bunch of input. Now, can I do this with a bunch of performance measurement, customer satisfaction, my occupancy of the market, and a bunch of why I can build a model like this? But in reality, okay, what are we really interested in a lot of time? Some X and some Y, or some combination of X and some combination of Y. Actually, we speculate. If I do this, the whole world will be organized in a certain way. And then my performance, Y1, Y2, Y3, will be in a certain way. And financial mathematics, they did that first. They call it portfolio theory. And then, of course, the portfolio basically said, my 401k or whatever, the stocks, a lot of time, if I have some oil stock, I will balance that with some chemical stocks. And whenever I have some genetic engineering stocks, I will balance that with some. Basically, you're trying to say that, okay, how I control the mean and variance, and mean and variance here, and to get things done. If you're a pure financial engineer, or you're in a business school, or you're in the banking industry, sometimes you don't really care what kind of X influence what kind of Y, because all you care about is what? Warren Buffett, okay, you know who he is, right? Throughout his life, his partner, Charles Munger, the old guy who just passed away recently. And all they did is that, we want Pepsi, we want Coca-Cola stocks, we want the Pacific Railway stocks, and they figure out how to package their money together, but they're not really working directly with Pepsi Cola, right? They just buy their stocks. So they're doing this kind of stuff just for that purpose. And then, of course, can I also talk about, and I can have a manufacturing guy or a Lean Six Sigma guy. All he care about is what? Oh, can I organize my manpower? Can I organize my resources, equipment, inventory, a lot of stuff, and then at the end, so I won't have any waste. I will have quality within boundary. But in reality, okay, that's why I kind of put this as a lip service at the very end of the semester, is that, and please bear with me, okay? I will try my very best to explain the optimization. I'm gonna use the term Lagrangian multiplier. You probably learned that somewhere before.
It's familiar.
Yeah, but the things I'm trying to show you here is, what if, okay, I'm really interested in is to figure out how to organize my X in such a way that I can make my Y maximize or minimize, okay? And how likely this will happen, or got a lot of usage in your career in the past, I will tell you this, okay? Right now, machine learning, the reinforcement learning, they're usually, okay, there are three things you need to remember. One is the delta t, how or horizon, how far you can look forward or look back. So in reinforcement learning, one is about TD, temporal differences, okay? And since I'm videotaping this, so you guys can rerun and figure that out. But the other things we're trying to do, they have this so-called online state response called SASA model, okay? And those are not really the key I'm interested in. The key I'm interested in is this. It's called Q learning. In Q learning, I will put it up and put it very, very important things here. For system engineering is a lot of time here. If I'm for salsa, you know what, like reinforcement learning is like driving a car or flying an airplane. Okay, you see something in front of you, you slow down. You see something on the right, you go to the left, and vice versa. You know, accelerate, decelerate, and you know, down slope, you should hit the brakes somewhere. Those things are control theory. Okay, and once it's done, it's done. System engineering or engineering management, we're not dealing with that kind of very straight answer. I'm not saying self-driving car is easy. What we're dealing with a lot of time is a bunch of yada yada, right? This whole semester, multivariate is a bunch of yada yada. We turn yada yada into a things. At the end, what we really like is Q learning. Is a lot of time we try to build a so-called lookup table. And what is this lookup table really good for you? Oh, you have this kind of X. Okay, your current state. You're in a very, very your state. You're currently in this kind of situations, and then on this side you can have some reward. Oops. Or slash punishment. And what's the reward? Christmas bonus. What's punishment? Pink slip, right? So what you're trying to do is how to control to I can write integral and said that let me integrate as many good things, which is reward, as possible, and get rid of any, stay away from any punishment as much as possible. But why are performance measurement? They can combine into reward or punishment. Those things that sometimes we can observe them, but we cannot really do anything about them. What we can do is a bunch of X. So, we need to fire a couple sloppy teenager, and get a couple grumpy old men. That will tighten or do something about. So we're doing X, but our goal is to accumulate Y. And so why we build a lookup table. The lookup table basically show you under this kind of X, okay, Y correlate in this way. So if you control your X this way, there will be a couple eigenvector will follow that direction and get something good. I'll find a one or two paper at the very end show you that how that kind of things can be done. It could be done in construction industry for design. They hate the most in construction industry is changing order. But how many times if you remodel your home, the contractor done halfway, you realize that, hey man, I just don't like the color, I don't like certain things, you want to change. And if you're very, very rich and you have a very, very compliant contractor, you don't worry about money, you don't worry about time, you can do it. But a lot of time changing order is what, I'm already in this state. And how can I use whatever I can do in order to make something I want to happen? So the lookup table basically, or this kind of quality table, basically said, under these conditions, what are my options? And what can I do to make things happen? I think I talk about this in a lot of our introduction class for undergrad. I said in system engineering, a lot of time, remember, never give your boss an essay. Always give your boss multiple choice. And what is multiple choice in this in nature is give him a lookup table. We're here. Our estimations were here. And you want to have this kind of Y1, Y2 accumulation. You want to accumulate this kind of reward, avoid this kind of punishment. So you need certain Y to happen. How to turn your X in such a way that the Y can be maximized. Okay, so again, my way of teaching is I'm not teaching multivariate statistics, even though I use it. I'm not teaching information theory or signal detection theory, but I'm using it. But I'm using it in a way I hope you can see that, at least in my head, to get a good job is not pure statistics, it's not pure optimization, it's data-driven optimization, how to use the statistics to find something good. And what I found that right now, Q-learning is hot topics. I actually tried to offer that class this semester, and I only have one outside PhD student willing to take it. And so I'm still trying to figure out if I can come up with a Excel, a little bit of SAS, or a little bit of R, then you can connect the dot. I probably will come up with a 4,000, 5,000 level of lecture for a course for this. But I hope you can see that if we consider what we're doing so far, it's very, very static. I give you a bunch of table. I let you use the table to build the logic, the causal structure, but we're not progressing over time. And here we're basically said that, okay, if I want to progress over time, okay, means what? Every few steps, I need to look. Hey, do I have this kind of X to maximize this kind of Y? However, do you think I can build a lookup table and say this table will be the secret of the universe? You have this table from now on. Just you can use this for throughout your entire career or entire product life cycle. Never happened. So what you're really trying to do is this, okay? Try to come up with certain things that you said that, okay, I told you guys I worked for airlines before. So when we come up with a flight plan, is okay, which runway take off, climbing to what and then from that point A, once I'm reaching the cruising altitude, okay, which route can avoid bad weather, avoid turbulence, and if you're in some hostile airspace, how to avoid the SS missile, and just stay away from troubles, right? And so the flight plan basically said what? From here, with this heading, this altitude, you can just monitor until you reach the next checkpoints. You change your speed, you change your flying, and also you have to remember your fuel consumption. So you say, oh, I have enough fuel, or maybe the pilot hates the most is that wrong calculation. They need to come down to refuel. So the lookup table is a table. You basically said that how far, what they call is horizon. Okay, I look at from here to the horizon. I need to find some landmark or checkbox and say, okay, from here, once you see the Bank of America building and now it's Duke Energies, and you know that, okay, I'm heading toward downtown. But once you say, hey, I don't see those anymore, then you probably need to find a new heading, a new landmark, a new lookup table. So bear with me with the math here, because that's part of the reason I kind of save it at the end of the semester, is that we're going to go through some very boring math, but the goal is how to build a lookup table, or how to build if I'm in this, what kind of combination can help me accumulate one-step reward, and then two-step reward, and things like that. Okay. Having said that, so canonical correlation. Okay, remember, it's not the correlations. I already know the correlations about all the input, or the correlation of my output. So what I'm saying is, up till now, the linear combinations, structure equations for your x or structure equation for your y, you can do it, right? There's a bunch of regression tree, okay? And of course, you can turn the regression tree into some Bayesian network, okay? But what we're really interested in is, if I have a bunch of x in a structure, or sometimes they said that they're in a manifold, and then I have a bunch of y in a manifold. My interest is not the x and not the y. It's the eigen of those x and the eigen of those y. And then how can I use this eigen and this eigen to make them form a formation? Okay? And in the drone flying, they have formation flight. They also have so-called leader-follower. And the leader-follower is basically, leader need to figure out that if I'm going in this direction, all the follower can follow well. Okay? So the interest is not X, is not Y. I already know X, I already know Y. I'm more interested in how X as a eigenstructure or causal structure influence my Y as a one like that. Uh, just double check. Have you ever heard or learned anything like this in other class?
I don't think so. I mean, as far, I think maybe we had something along this line with experimental design. So, like looking at all your different variables and looking at the interactions, and it's like, okay, well, if I modified, if this variable changes, then how does this change my interaction?
That's. I don't know if you learned from Agnes, right?
Yeah.
Yeah. I don't know if she covered this. Is so a bunch of X can I form a response surface.
Right.
So I have response surface 1 and response surface 2 and response surface 3. They all function of x1, x2, x3. But then, there's no free lunch. So you can consider I have 3 response surface, and you can consider I have 3 crying baby here. So our Dr. G, kind, try to make baby 1 happy. Turn the room temperature down a little bit, humidifier up a little bit. But when you try to optimize everything to make baby 1 happy, do you think baby 2, baby 3 will be happy?
Probably not.
So now, well, maybe they order the same. But so the things you're trying to do now is almost like you have the 3 baby are 3 voting mechanism. You have to find a way to let all 3 vote for you. But if you cannot make 3 vote for you, you should at least make 2 vote for you. And so there are so-called multivariate response surfaces. And I don't think she covered that. But and the one I'm trying to ask you to think about is Pareto frontier. Pareto frontier, here, Pareto frontier. Okay. And we did one at the beginning of the semester, remember? You have quantity 1 or quantity 2, and then if you want to go in this direction, it means that this is only in 2 dimension. I'm holding a flashlight, looking outward. Nothing better than what I have. Then I know I'm at a frontier. But if I'm at a K or N, I look outside. I can probably see D, E in front of me. And then I know I haven't reaching the frontier. So I can keep pushing that. And that's the things that I think this is a good things to remember. Okay. However, okay, I think I said that in the beginning of the semester. Looking at a frontier, sometimes it's a science fiction. You believe people won't change their mind. Customer will be always happy. The 3 baby, you can find a frontier to make 3 baby happy. In reality, people change their mind from time to time. So those frontier or those direction, you look, just like those eigen you look at. Sometimes you're basically said that, how can I find a way to make certain things good enough so I can switch my directions into something I can find better trade-off. So now it becomes a kind of step-by-step things. Oh, I need to get into the best job or best management position. I need stat, I need OR, I need programming. But do you study three things simultaneously? No. So you basically say, oh, this two can be complementary. Let me do this, reaching certain steps, and then you said that, well, this is good enough. Let me switch my attention to something else. But the minute you start doing that, you basically start building your lookup table. Where am I right now? Do I really have enough of certain things? So I don't need to worry about those things. Let me switch to another one. But no matter how you do this, changing order, switch, you need those icons. And I probably said it in the previous lecture. I argue with my buddy in OR or with Dr. Lim. I don't believe human ever really using objective functions to reach the optimum. We use them like lighthouse to give us guiding direction so we can move and say, oh, so if I do this, I can move Y into that directions. So I'm start manipulate this and said, okay, do I have enough of this? Okay, now this is safe. Don't touch it. Now let me, without hurting my current state. Or sometimes I'll say that let me sacrifice a little bit. I won't mind for young people, right? A lot of time you guys will say that I don't need to eat that well. I don't need to have fancy clothes, but I would like to have a nice truck. Yeah, and for certain girls, they probably will say that, my certain things that, well, I have to be careful, get into political incorrect troubles. But what I'm saying, there are gender differences. We're looking for something differently, but that is why this eigen is important, because once you figure out the eigen, you start saying that, okay, at current state, what are my options and what can I monkey around with? Okay, now getting back here. So I'm not talking about the correlation of X versus a bunch of X or correlation of a bunch of Y. I'm talking about the correlation of a bunch of A time A prime, okay, A transpose X and B transpose Y. So this is a bunch of X yada yada. Here's a bunch of Y yada yada. But this is a bunch of X yada yada organized by A, or a regression of A. And then here's a bunch of regression of Y, and then here's the variance, and here's the variance. And then, of course, this is kind of like, if I don't tell you anything about X, I just give you a bunch of X transpose X, B transpose Y, and just say, here are your new X and new Y's, just deal with them. You're not looking at the raw, you're looking at the transpose, okay? So if this is the case, covariance of this, since the transpose is the term that in the front and in the back, so I can have this as the A transpose sigma xy. So I'm looking at the sigma xy. Okay, and so what is sigma xy? So the original xy is there are some x correlation, some y correlations, and some x and y or y and x structure like this. So we just partition them into this, this, this. Now, those things I cannot touch, but what can I do to organize my x and y such a way that I can have some story I can tell, okay? And underneath here, okay, inside, covariance is the summation of a bunch of area. The variance are a bunch of square. And then, so correlation is just rectangle area over the square. okay? And I would like to make this as big as possible. So in other words, is that I'm interested in come up with a story through organized X and through organized Y, so the eigen and eigen can be as correlated as possible. Okay, and without we can assume that the correlations, no matter how you play with it, inside A and B is 1. Okay. Now, next, here is the Lagrangian multiplier. Here is the objective function I would like to maximize. Agree? And here is the constraint. X by itself is 1. Y by itself with the B is 1. So Lagrangian multiplier is basically said that if I can find, let me see, Lagrange multiplier. Okay, here we go. So Lagrangian multiplier is usually look like this, okay? You basically said this. I have a X I would like to maximize or minimize. And I have so F is something I would like to maximize or minimize using these equations. But they are under a bunch of constraints of G. G are a bunch of constraints. So when I try to say find a maximize of this, okay, first thing first, okay, if lambda is 0 means what? If lambda multiplier equal to 0 means that none of the constraints play a role. Agree? So your objective function is or depends on your fx. So fx, first derivative equal to 0, second derivative is greater than 0, holding water. If it is less than 0, is upside down, as it is. But when we do this, okay, I would like to say that I'm navigating this f. What if lambda play a role? The lambda play a role means that some g will interfere with my my objective function value through lambda. Agree? Mm-hmm. Now, if that's the case, what I would like to do is what? Find a x, okay? When partial I don't know what's this pronounced, but this loss function, partial derivative of x equal to 0 means what? I would like to find an objective function, f, first derivative equal to 0. And all the g, the first derivative, also equal to 0. Means that no matter my objective function or my constraint g, they're all reaching some sort of top. Okay, so and then at the same time, I would like to have the lambda equal to 0. Lambda equal to 0 means what? Lambda can increase and decrease. Lambda increase means that they're influencing, the constraint influence is very, very high. And lambda is less than 1, the trade-off is not very, very high. So this also, using this to say that I would like to find a loss function such a way that all my objective function and all my constraint, okay, they are reaching a equilibrium point. And then, so they're equal to 0, in such a way that all the gx can be locked. Okay, so now that's as far as I'm willing to go with Lagrangian multiplier. If you want to learn more, you can go back to DFQ, and some of the stuff will tell you more fancy approach. But here's my loss function g. Okay, so Lagrangian approach, objective function equal to 0. A transpose sigma x y b is my fx part. I would like to make this guy as big as possible. Right. Agree? But at the same time, this two constraint, okay? And I'm just using half of lambda 1, half of lambda 2, because, you know, I only have two constraints. Each one of them contribute, let's say, 50-50, okay? Well, you can weight it differently, you know, 1/3, 2/3, but now let's just consider equal weight. And then inside, this equal to 1, so this minus 1 equal to 0. And I would like to have this constraint as close to 1 as possible. This as close to 1 because they're supposed to be equal to 1. So by doing this, okay, now we can say that, hey, find me the A term and B term. So it's almost like structure equation model. Find me some parameter of A and B in such a way that when they organize, I can do formation fly. So first derivative or second, a partial derivative for A and for B equal to 0. Here, if for A get cancel out, summation x, sigma x y b left, and lambda 1, the A part 1 left, okay, and then here's no A, so this is all equal to 0. This equation, partial respect to A, become the partial A, partial G, partial A, get this equation. Partial A, partial B, get this equation. So far, so good? Yeah. So after you do that, you can, resolve and just say, okay, where's my lambda 1? Move this to the left, move this to the right, and then divide it by this. So you will have lambda 1 and lambda 2 resolve. And so, but you look at lambda 1 and lambda 2, A transpose sigma x b y b, lambda 2, B transpose sigma y a. So this is just, changing the sequence, but the same thing. So lambda 1 equal to lambda 2. And if lambda 1 equal to lambda 2, then we can rewrite the above equation, becomes summation sigma xy minus b, this equal to 0, and this equal to 0. And just, so there I have two simultaneous equations. So far, so good? Mm-hmm. You with me? Two simultaneous equations, and I can, use one and plug them into two. So first one, here, back here. So if I move the lambda and b out, so lambda b becomes sigma inverse yy, sigma xy times a. So how you solve, here, this equation is still fun to look at. Okay, you can start from the second equation and going back to the first equation, but basically still got a very strong flavor of what is my A and B relationship. Depends on how you're gonna correlate x and y, but at the same time, either you use y as base, then b on this side, or x as base, and then you plug in the second equation into the the first equation conversions, you get into uh, this sigma xy, y inverse, sigma xy a equal to lambda square, because you have lambda plug in, so lambda again, lambda square, sigma xx and a. And once you do that, okay, you can play the same, you can find lambda square should be an eigenvalue, and a be the related eigenvalue vector. And then, of course, you can reverse, play the second equation first, and then second equation second equation first, and first equation second, and you can similarly reaching the same lambda square. So by doing this, you can just say that find me sequentially. This is almost like doing what? You're still doing your scree plot. You're doing your scree plot not at a x, not at a y, at a bunch of x eigen, a bunch of x y, at the higher level. Okay. Something in system engineering is important here to argue. In physics, we know that particle physics, okay, your quantum or this hit that, okay, they have a lot of time very, very different rules from Newtonian physics, driving a car, flying an airplane. And then astrophysics, extreme large scale. They also have this black hole, this and that. They're following their eigenstructure, the way how they organize in a very, very large scale, very different from the Newtonian physics. And why I'm saying this is that a lot of time, okay, I learned this over the years, is that sometimes you look at X, you said, oh, well, I'm organized all the students' effort. I organize everything that I need to organize. And Y, all the performance measurement. I'm doing this to make Y1 good, Y2 good, Y3 good. And at the end, how come, my grade or my performance measurement is at the satisfactory level? They didn't give me excellent. And then I look at the, my benchmark. He didn't work as hard as I do. He didn't burn the midnight oil. How come he got a lot of stuff done? And then I realized this is a lot of time is when you do multi-dimensional optimization, scale matters. If you look at things too detailed, we say devil is in the detail. You look at things too detailed, a lot of time you cannot zoom out and look the big picture.
Macro.
Yeah, but then sometimes you look at everything at a macro scale. You could miss the good stuff in the in here. And did I mention how to watch a movie in this class? Okay, I'll say it. Just lip service. What's your favorite movie?
Fast and Furious, the whole.
You want any movie? Just name one.
Fast and Furious 5.
Okay, I don't know that movie. Okay, but you might have seen that movie more than once, right? So you understand the storyline, you understand everything, right? So sometimes play the movie one more time, if you have the DVD, without volume, without sound. So now you're basically said that, okay, if I'm the director, should I have a zoom in here for the facial expression of the actor or actress, or should I have a zoom out, pan the camera from left to right or right to left, or top down or doing something.
We did talk about this.
Hmm?
We did talk about this.
In this class?
Mhm.
Yeah. So here is the time for you to think about your organization of your X and your Y. Sometimes certain situations, the vector you need to worry about to organize is too detailed. And sometimes you play with this just too big, and then you don't. And so I will say this is a continuous effort. Keep building the lookup table, but here is how usually. Okay, this is the procedure. You build your objective function, you turn them into a Lagrangian multiplier expression, and then you do a partial derivative, turn them into simultaneous equation, and plug one into another until you can solve the two equations. And once you solve the two equations, okay, then you start prioritize them. First set, what is the best best organization of my X to maximize my correlate best with my Y? What is the second set or third set? Okay, once you get that done, okay, at the end we'll call this, oh, U is my new world, V is my new world, and my correlation is my Z1, and then you move to the second pair and the third pair. And let me be honest with you, if you want to get your Christmas bonus, never talk to your boss about Lagrangian multiplier. I wouldn't do that. What I would tell him is this: the first pair, this organize a bunch of X, and here is my scorecard, a bunch of Y, and with B, and how I can correlate the two together. Okay, and here is the famous example. You guys can find this online anywhere. They ask the executive for job satisfactions and how to organize this whole thing together. And there are characteristics. You give this one is in the right spot. Yeah, you give people feedback. Okay, you give task significance. You give task variety, and then here are a bunch of things of X, and here are a bunch of Y things, and then now the game is not to build as just, well, of course we still can build causal structure and causal structure, but before we build causal structure for causal structure, first you're just trying to figure out what kind of linear combination of characteristics can make my Y look big or look small, and figure out the vector for vector, vector for vector. Once you have the vector, it's almost like once you have the discriminant analysis and our C curve done, and said, oh, take care of this, people will buy computer or buy your cell phone. You go back, right? You don't go back as a plug and play, then that is not good. You go back and say, I wonder why. And then figure out if you can build a causal structure. Ground is wet. How to build your ground is wet structure versus this, and figure out how to get that done. Okay? And I give you the SAS code here, Prac and Core, and let's do that next Wednesday to go through this, and you can tell a bunch of A, a bunch of B, and structure done. And once you have the structure done, first set of something something relate to something something, and that's your U and V, and can have this done. And I'll also say this, okay, my personal experience, this 5 to 7, when you build a causal structure, three-way interactions, it's hard to explain. When you do this, I usually found that 2 to explain 2, I probably do a decent job. Once beyond, first the table become too complex. The lookup table is not good enough, but this is the way how we should go. Okay, would you like to? I'll tell you what kind of homework. Well, let me put it this way: if you don't have a term project, okay, what kind of final exam problem I can do is, can I have all this and using the eigen to build a two-dimensional mountain of how those 5 variables organize the top 2 and build a bell shape. And this 7, can I build another bell shape? And then what I can say is that, okay, how this bell shape eigen organize with the other eigen. But then here is the monkey of the Wasserstein divergence. Yeah. So I'm basically said, okay, if I add another variable or reduce another variable, can I change the shape of the distributions? And what I'm basically trying to do is, what can I do? Change my task variation, or this can make my entire distribution shift a little bit. The shift, okay. Of course, the cost is to moving things around. But what will be the things here is that make the correlation even stronger. If I can, wobble or switch this a little bit, make the mountain shift 90 degree, 45 degree toward 1 o'clock positions, a little upward or rotate a little bit, then I can make the whole things looks better. And so now you basically said that, okay, how can I do my input to make my output looks good? And I could do it the opposite way. This is the ideal distributions, okay? But your distributions of your performance is a little bit off. Say, I want to have my car behave like a BMW, but I'm not a BMW. But I would like to fake to be like a BMW, look like a BMW, sound like a BMW, maybe speed not as good as BMW, but I would like to do that. So now I'm basically first figure out the length, the divergence causal structure, make this two distribution looks a little bit fake a little closer. And now I turn around and said, in order to fake that well, what should I do over here? Give people more autonomy or task variety, such a way that I know I'm not BMW, but in order to fake as much as like a BMW, what should I do over X to do that happen, to make that happen? Now, you basically build a lookup table. Always find what they call benchmark. Okay, I would like to look like this. I want to look like Rolls Royce. What should I do? And to do that, okay. So, yeah, I don't want you guys stop at this class after the semester is over. This stuff, I think, got its own life, and I'm not a fan of ChatGPT, but I will tell you this: ChatGPT only give you some logic of imitation, but sooner or later, how to dissect your data and figure out that what is the logic behind it, and I think that's the only way you can maintain your job security. If you just use ChatGPT's answer as your own answer, the layers is too shallow, and you can easily get caught for that. So what's my plan? finish this, and I give you I always upload the SAS manual, this slides, and when this is all done, we'll go through, I think probably next week or after Thanksgiving, only have 1 or 2 lecture. I'll go through all the lecture notes and double check, make sure that you have all the tools in your toolbox. Okay? See you next time. Yeah. You want to do one more homework or no more?
It's up to you.
Really?
Yeah.
Okay. Let me find something not labor intensive, but you can connect the dots. Okay. Yeah. Okay.